Good soul. This is astronaut Praveen Kumar from Habitat Marte, Mars Analog Mission 166, Alan Shepard mission. Happy to join along with my fellow astronauts, Inia Pragati, Adrian, and Professor Julio. This is about our mission in Mars. I would like to take you through our destination, new home, Mars. This is our habitat in Mars. It has 7 major infrastructures comprising of launch pad, main station, greenhouse, hospitals, sanitation, power station, and auxiliary units supporting the main station. So this is about the power station. Let's deep dive into the overall facilities. As I mentioned, the launch center connected well with the main station, with a health facility, greenhouse, engineering facility, sanitation center, and the power station. MOXIE is the Mars oxygen in situ experiment, which produces the oxygen in situ in Mars. We also have the solar farm and kilopower energy plants, which are quite interrelated with the power station. And this is where we are going to focus about our discussion today. And indeed, it's a very special day today, being International Astrology Day, Astronomy Day. And we are going to start with the power station with a detailed overview in terms of internal design, where we are going to talk about the overall aspects of the power station habitat, how the design is going to be. This is going to be divided into 3 different floors. And we will have a deep dive in terms of internal design, followed by the missions and technologies necessary for the operation of the installation, possible resources which either we would be transporting from Earth or in situ resources which will be kind of produced in the Mars. Then about the organizational structure, how the power station team is structured in terms of the positions, profiles, and the duties. We are going to talk about astronaut training programs, how the astronauts are continuously being trained. And there are various means to train them, including the videos. And of course, the resources which are required for the power station. Guidelines which are important and specific to the facilities and the entire station. Further, we would also be looking into the specifics of the protocols and the routines of the facility. The protocols mainly on the safety, which is very critical in terms of the power station. We'll also be looking at the protocols for the occupancy in terms of their upkeeping and entertainment in general, and also in terms of very specifics about the energy production. The protocols also includes 3D printing, which aids in terms of any of the components to be produced, any of the auxiliary problems in terms of any of the components failures, we will 3D print them. And we will also be looking into the technologies and outputs that would benefit back in Earth. Guidelines to be applied to the daily life on Earth. And the most important thing, the impact of all this endeavor towards sustainable development goals. With this overview, let's look deep dive into the power station. We'll start with the internal design. Basically, the transportation from Earth to Mars would be happening through launch vehicles like Falcon Heavy or spaceship kind of vehicles, of course, including the SLS. So these are the rockets which are primarily of big in nature in terms of capable of carrying a very high payloads to the tune of targeting about 15 tons per shipment. And we are targeting close to about a 30-ton shipment for the habitat to start with. And that's where we would see the design. And we are talking about a power station with 8 meters in diameter, comprising of 3 floors. Here is an overview of the power station, which was created using an help of artificial intelligence tool, OpenArt AI. And this represents a complete habitat for the power station. including the ground floor, the first floor with critical facilities comprising of battery storage as energy storage devices, backup power strategy, which comprises of multiple energy sources, thermal management, safety, and including the safety protocols and safety devices. It also comprises of high voltage DC master controller and the fuel cell stacks, kilopower terminal junction, where the kilopower unit will be situated outside the power station, and the power is being transmitted back to the power station first floor. And we also have the charging units for XEMU and EVA. XEMU is the exploration of the extra mobility vehicles, and also about the EVAs. So basically the rovers, EVAs, and the XEMU will be charged from the first floor. And now we were looking at the power monitoring and control station, which is situated in the second and third floor. Again, this is a rendering from an AI-based tool, which is OpenArt, which was very specific to this particular requirement of the various devices and the control room, what we have in our habitat. The second floor comprises of master control room, where the central control of all the other major stations are being handled. The remaining 6 stations, which we have seen in the beginning. And we also have the station-wise power monitoring, auxiliary power device, critical facility monitoring. And again, the recharging happens both from first floor and second floor. First floor is basically the storing of energy through auxiliary devices, and the charging control is happening at the second floor. And third floor, we have the energy experiment lab, and the maintenance lab, which is very critical in terms of the continuous operation of the entire facility. We also have hydrogen backup tanks and the MOXIE control station, where the oxygen is being generated and the life support is being taken care from the control station. We also monitor the radioactivity in terms of the kilopower stations. So currently we are targeting about 4 to 5 stations, but probably during further missions, we will be adding the kilopower. Here, the kilopower is the base load, so monitoring the radioactivity is very important. And we also work on the launch station power backup. The third floor comprises of the launch station power backup and the blackout control strategy communication room, which is a very vital room in terms of emergency situation handling. And so with this, all 3 floors, first floor, second floor, and third floor of the power station, we have seen the overview and the various units which are part of this. This is one of the older generation habitat plan for reference, how it has evolved over a period into the current generation. And would like to take you through the complete power infrastructure overview, which comprises of various stages. Stage 0, stage 1, stage 2, stage 3, and stage 4. And you can see various combinations in terms of stage 0. It is combination of battery, fuel cell, and photovoltaic, which is a solar-based energy source. And stage 1 again with solar, battery, and fuel cell. And in terms of stage 2, we have nuclear, solar, battery, and fuel cell. And stage 4 comprises of, again, predominantly with nuclear and solar, with the battery banks. Likewise, the combination is quite interrelated. And with this, we could see it is interconnected to the entire habitat, connecting the basic habitat requirements to the basic science and engineering center, life support center, advanced habitat research and science units. And it's also powering the in-situ resource utilization units and the external explorative units and EVAs. So here you could see 3 different colors. The blue shade showing about the low voltage DC current flow, whereas the purple one shows about the high voltage DC current, and the black one is representing about the AC current in terms of the overall power infrastructure. Let's deep dive slightly into the power sources. So we are talking about solar power generation. Solar power, as we might see in terms of Mars environment, we have challenges in terms of having a solar availability, which is close to about 50-60%, usable solar energy. The photovoltaic arrays optimized for Martian conditions is very critical in terms of the design, in terms of the environment, dust, and other conditions. The spectral efficiency is critical to the overall energy efficiency of the system in consideration to the Mars atmosphere. Deployment strategies to maximize, in terms of isolation exposure, and also the potential for concentrator photovoltaics. This is one other means apart from the panels to enhance the power density. Here, predominantly the solar panels are being ultra flexible panels, which are also being produced in situ using special inks, which can be 3D printed, and we can produce additional solar panels. So of course, we have few of the base load coming from Earth, and we print further solar panels in our habitat. In terms of energy storage systems, these are very critical as we have to store energy for situations where we don't have sunlight in the nights, in the situations where we are completely the production of energy from other sources are depleting. So the backup energy is very critical. So in terms of high energy density batteries, quite a lot of multiple technologies are being taken care here in terms of lithium ion, in terms of solid states, flow batteries, and also lithium metal batteries. And these are systems which are highly efficient in terms of their operations and operating very specifically suited for the Mars conditions. Thermal management of these systems are mitigated to the temperature extremes, considering the Mars conditions. And the redox flow batteries are primarily used in terms of scalabilities, considering the longer duration missions and the energy storage needs for the mission. In terms of backup power strategies, contingency planning for extended dust storms and equipment failures is one of the critical tasks. Evaluation of small modular reactors, basically the SMRs, which are for the autonomous power generation, is very critical. We are also exploring in terms of supporting the kilopower for the rovers and the mobile laboratories, which we would be seeing in detail. Prospects of in situ resource utilization is very, very critical in terms of life support. One of the major tasks for the power station team is in terms of the maintenance and repair protocols. As a chief of power station, the development of autonomous robotic systems for infrastructure upkeep is a very critical one. We use extensive artificial intelligence along with robust manual approach, deep learning algorithms for backup strategies with manual overrides or a natural thought process towards improving our ability to have the effective, efficient running of these power stations for the entire habitat. Remote monitoring and predictive maintenance algorithms continuously being improved over time. And we use effectively the 3D printing for on-demand part fabrication, including solar panel production and other key critical components. You can just see an overview of the solar panel being deployed, both in terms of panels as well as concentrators across the habitat. Now let's deep dive into the missions and technologies which are necessary for the operation of the installation. Power generation from multiple sources, including kilopower, which is nuclear based, solar, biodigesters, and other from other stations as well. Management and control of consumptions in terms of how effectively are we producing and how effectively are we storing, and in terms of utilization, how are we effectively using this limited power what we have. We study the detailed plan in terms of the energy supply versus demand situation, and accordingly we just handle the need for energy to charge the electric vehicles that will be used in the EVs and across the power station. Make simulation and safety in terms of energy supply for these vehicles. We also work on the system operations and maintenance, repair of all energy hardwares. Now let's have a deep dive in terms of the various sources, starting from solar panels, nuclear fusion, hydrogen fuel cell, kilopower energy plant, structural solar windows, energy storage devices, backup energy devices, and MOXIE. Just as an overview, the power sources are generally classified into two, internal and external, with the external being the beam, solar, and wind, and internal being chemical, nuclear, and thermal. This is an interesting area where we work in terms of improving the efficiency across all these different power sources. Now let's have a deep dive into the kilopower reactors, which is called as Christie, kilopower reactor using Stirling technology. These are the devices, if I am able to show the pointer. Here we can see each one is a kilopower reactor, up to 10 kilowatt of each capable of supporting for 10 kilowatt of energy power. And this is how it looks. It's folded when we shift from Earth, and it is deployed. And these are the radiators for releasing the excess heat. And we have the device which is located here. And all these multiple devices are interconnected, and the junction goes to our power station. This is a deeper insight into the kilopower. The criticality comes here with 10 kilowatt weighing up to 1,500 kgs of mass. And we have these units, which are the Stirling generators. And we have nuclear fusion, which is happening over here. And this is the components, various components. And the picture which was taken in Earth, which was kind of during the testing phase, where we could see the nuclear reactor portion, and then the thermal generation, which is producing the heat and running the system, and which is producing the electricity. Let's look at a short overview in terms of
each component is watts. The goal of the test is to confirm the system's predicted performance. The reactor core is a cylinder of enriched uranium that is 6 inches in diameter. A beryllium oxide reflector will surround the uranium core. A single rod of boron carbide is used to turn on the reactor. The reactor uses well-established nuclear physics to self-regulate the fission reaction, and this feature eliminates the need for a complicated control system. The reactor uses nuclear fission to produce heat, which is delivered by heat pipes to power generators, known as Stirling inverters. A radiator is used to keep the Stirling inverter cool.
Yeah. This short overview, just to give an idea in terms of how the kilopower works. Let's look into the some of the insights. This is the first nuclear powered operation of a truly new fission reactor, which is very compact. And it's working as a base load for the overall habitat, which is very critical in terms of supporting all the major devices. And it also supports in terms of a passive reactor operation of kilopower, right from 1 kilowatt to 10 kilowatt. And it's very cost effective in terms of considering the various other options. And it is also useful in terms of long range missions, as well as long duration missions. It's truly an astounding space fission capability. Of course, we are also working on the nuclear fission, but currently nuclear fission 10 kilowatt kilopower is the base load for a power station. An overview in terms of the various events, scenarios based, and the performance in terms of the reactor startup, the steady state performance, loss of coolants during the operation, and maximum coolant temperatures, the converter efficiency, converter operations, and also in terms of the electric the turn down ratio, which is 2:1, and whereas the performance is more than 16:1, which exceeds our expectation. In terms of the energy storage, an overview comprising of various missions in terms of orbital missions, aerial missions, and specifically human precursor missions in various aspects. So there are multiple choice with various benefits. These are some of the needs which has been collated in terms of the energy density, the depth of discharge, the SOC, the thermal conditions, and also in terms of their life cycles. Yeah. When it comes to Mars specifically, there are quite a different energy storage types in terms of primary, rechargeable, with respect to their energy parameters, life parameters, and environmental parameters. And these are some of the aspects where we are talking about high specific power, which is about 3000 watt per kg, and having a life cycle of more than 1000 charges and discharges. In terms of the possible resources to be generated back in Earth or in in situ in Mars. Of course, we discussed about solar power. We discussed about carbon dioxide based electricity generation. Also about Martian mobile laboratories, uh, exploration, extravehicular mobility units. So primarily, we will be deep diving into all of these topics in our forthcoming slides. Of course, the solid energy is primarily being used by Gen 3 lithium metal batteries. Solar power, due to the relatively low air pressure and limited solar irradiation, the challenge with respect to solar power as only up to peak power supplement is what we have considered. The space-based solar power function compared to Earth in Mars, it's going to be only a partial load, which will be helping us in terms of compensating the peak load conditions. Yeah. With respect to the Martian mobile laboratory, this is one of the key aspects for driving the complete experiments apart from the EVAs. These mobile labs are used to extensively do a lot of researches in terms of identifying the water and water-based sources where extensively being used to convert the stored energy from the kilopower is directly used in water electrolysis, splitting water into hydrogen and oxygen. And oxygen is being in situ produced for the astronauts as well as for the habitat, and also for other critical experiments. And the hydrogen is being stored for various purposes as fuel, which can be again produced as energy using fuel cells. Again, these are some of the representations which talking about expanded vehicles, which are much bigger than our current rovers, which are quite light and capable of doing limited experiments. Whereas these Martian mobile laboratories are capable of handling much bigger experiments and longer distances away from the habitat. The XEMUs, again, very critical in terms of supporting the astronauts in terms of performing their activities outside the habitat with the harsh conditions, and capable of withstanding up to 6 hours. And our latest generation is capable of extending up to 10 hours. And we are talking about the various options in terms of availability of logistics, resupply, and also availability of in-situ resources. These are very critical in terms of balancing what we have versus what we have to carry. And the atmospheric conditions compared against lunar versus Mars, which clearly talks about the various conditions with respect to availability of water in terms of atmospheric pressure and in terms of the minerals and other resources available. With respect to the habitat and the other aspects of how the various stations are interconnected is represented in the right through C, which talks about the cargo, the loop closure, and the in-situ resource utilization. Now, next to kilopower, the main focus of today's discussion is also about Mars oxygen in-situ resource utilization. Experiments which are very critical in terms of producing onboard oxygen. The intake air from Mars, which is predominantly carbon dioxide, is taken, and carbon dioxide acquisition and compression is happening, which is followed by the oxygen production through solid oxide electrolyte electrolysis, which converts back to the composition measurements, and oxygen is being produced along with carbon monoxide and carbon dioxide. This unit is a very compact unit. We're quite capable in terms of producing a significant amount of oxygen. Let's look at the capability in terms of, so initially this is being mounted in the rover, and now there is a bigger unit which is also capable of producing the oxygen for the habitat. The initial unit was close to about 17 kg on Earth, and it can produce close to about 10 grams per hour, which is very low. But now the bigger units are capable of producing 10 times more than this, which is 100 grams per hour. Operation time, 1 hour of oxygen production per experiments scheduled intermittently over the duration of the mission. Whereas now the continuous operation is being targeted as oxygen source. In terms of overall sequence, it's carbon dioxide acquisition and compression, called as CAC, and solid oxide electrolysis, which is XOFC, and process monitoring and control through the gas exhaust heaters and oxygen sensors. This is an overview in terms of how the carbon dioxide from Mars is being kind of separated out and oxygen is taken out, and still the remaining carbon is captured for other uses in terms of Sabatier process, where the carbon dioxide plus hydrogen is also used in terms of producing water. Now let us look into the launch center overview, which is well connected with the power station in terms of the energy perspective. The control and production of propellants. Basically, the hydrogen production is happening in situ in Mars. The control of launching and landing of rockets in terms of communication as well as power supply. Evaluation and unloading of payloads. We also examine the new visitors, astronauts, quarantine them, and in terms of aspects related to new crew entry. Mission control for landing and launching. Launch vehicles predominantly nuclear power. Considering the long distance from Earth to Mars, nuclear propulsion is being predominantly being considered, with nuclear thermal propulsion NTP and nuclear electric propulsion NEP. And we could see the nuclear engine, which is ultra safe in terms of nuclear technologies. This is an overview of the launch vehicle with launch station energy management using the nuclear thermal propulsion. We could see the vehicle launch vehicles. And just an overview in terms of how different the nuclear thermal propulsion versus nuclear energy propulsion. Nuclear thermal is quite interesting and the value proposition in terms of current scenarios, whereas the nuclear energy propulsion gives quite consistent long distance efficiency, but with a very lower thrust levels, whereas the nuclear thermal provides higher thrust capabilities. In terms of the conditions where we are seeing the launch station, which is outside the power station, which is closer to the main station, where we are seeing a relaunch, reusable launch vehicles being considered for various further missions. And this is again a overview in terms of a image which is being produced by artificial intelligence aided tool, which is being representing about the various launch options from the launch center and the various other substations. Let's have a look in terms of what are the different materials being explored in terms of the nuclear electric propulsion systems, where we are talking about various other fuels being used, hydrogen, helium, whether being it electrical propulsion or thermal propulsion, and also how to reduce the travel days from Earth to Mars, from being 180 days to nearly almost 50 days. Yeah. So nuclear propulsion is going to be a key for easier access between Earth and Mars and frequent travels, which will help the overall habitat in terms of equipping it quite interestingly. This is about the proton exchange membrane fuel cell, which again uses hydrogen and oxygen. It produces byproduct water and also produces the energy. So that's where MOXIE, which produces oxygen, and in terms of water, which is available in Mars, which is going to help us in terms of producing the hydrogen and oxygen. And again, effectively using back the hydrogen and oxygen to produce water as well as electricity. So this gives us quite a closed loop in terms of various options for energy management, and also providing the life critical oxygen and water, along with the fuel, which is important in terms of hydrogen. Now let's focus on the management. As Chief of Power Station, I have technicians, researchers, and engineers supporting in terms of the power station. As Power Station Chief, I need to check the crew's routines, maintain contact with other chiefs and commander, ensure the success of the center and correct operation, management of the overall systems, decision-making, resource management, and coordination of tasks with the power station team members as well as with the overall station. We have our researchers who are working on development and study the new methods of energy generation, develop the tests for new equipments, study the design of new equipments, and conduct experiments. Engineers, they take care of designing the operations and procedures, define and apply the security procedures protocols, directly work with the technicians and research astronauts, and keep a log of events in the station. Technician supports on the critical maintenance and repair of the equipments, supervision of the correct operation, preparation of the necessary equipments are the key roles of me and my team. In terms of astronaut training program, as it's a critical function, all the astronauts are being continuously trained on various aspects of the power system, right from electrical electronics routine checks, energy research. We also conduct mock drills in terms of blackout strategy planning and backup energy predictive maintenance, electrical and electronics based first aid, and also including the blackout strategy first aids. Brainstorming and problem solving is a continuous exercise given to the team in terms of innovation, research, and the maintenance aspects. Space psychology, mindfulness, well-being, communication skills, and integration with rest of the other overall habitat team members is very crucial. The astronauts are also being trained with various options of training methodologies, including videos, which covers various gravity-based influence of G-forces, and also in terms of remote conditions like storms, and if there are any situations where the astronauts have to go out for maintenance of equipments like kilopower, solar panels, and things like that. In terms of the resource requirement, this is very critical in terms of how we balance the overall energy mix in terms of their weight consideration, their energy efficiency, and the overall energy and power demand. For the overall habitat, we are considering close to about 12 kilowatt as the base load. And for the life support system, which includes the air circulation, water purifier, waste management, and thermal control systems, it's about 5 kilowatt. And the essential supplies, which includes food storage, water storage, and other consumables, it takes about 1 kilowatt. And the various instrumentation devices takes about 2 kilowatt. The EVAs and the mobile labs on the wheels takes about 5 kilowatt. And for the crew, it takes about 1.5 kilowatt, which comprises of their respective tasks, including the experiments and various activities, including the overall consumption. Considering a 5% margin of variations and inefficiencies, the habitat consumes close to about 50 kilowatt, considering a 35% of factor of safety. And some of the guidelines to be provided to other facilities and complete station. Considering various stations use different power levels, it's important to balance these power in terms of how they are being used, when they are used, are they being used simultaneously. So that's where the load sharing is being closely monitored. From the main station, we monitor the power supply, oxygen supply, and recreational area. And engineering center mainly on the instruments, equipments, and storage facility. Sanitation center basically on the water recycling, oxygen regeneration and cycling, composting biomass aspects, and also in terms of recycling of the waste. And in power station, we focus on the supply and demand situations, both at energy level and power level, and the health center primarily on the exercise routines and other aspects which consume certain amount of power. And green station primarily on the lighting systems, water circulation systems, and temperature monitoring. Now let us look into the protocols. Specific protocols to the power station, regular contact from other stations, and also from Earth via direct receiving station DRS. We need to maintain that, and the structure of the center should be monitored regularly for E&D and basic parameters. Nuclear rods, we need to check regularly for kilopower, which is the primary source of energy. And it's important that when we do any maintenance with the kilopower, the power is being balanced with other energy sources. We also report the data in terms of maintenance and backup regularly, both to the overall main station as well as to the center at Earth. Tools and equipments needs to be kind of maintained properly, and we also work on the various converter systems and maintain them regularly. In terms of first aid, it's very critical for the power station. We also focus our team's training in terms of basic first aid skills on CPR, and also in terms of stabilizing patients in terms of emergency situations, and provide immediate medical care for them. You also need to handle medical emergency situations, which can be both purely medical related, psychological related, or can also be related to electrical and electronics related events. So where we also participate in conducting mock drills. Medical equipments familiarization is also being given to the team members of power station, which includes medical kits, diagnostic devices, and various medications. In terms of space-specific medical considerations, each of the team members also receive specific space flights, including trainings on radiation exposure, muscle losses, bone sickness, motion sickness, and also in terms of maintaining their health conditions regularly. Of course, we focus on various other aspects in terms of relaxations, meditations, physical exercise, observing the spending time in various other stations like greenhouse, and also in recreational areas, listening to music. And of course, our team members also do the sky glazing on the top floor using various telescopes which are available in the greenhouse. Specific protocols for energy production. We need to balance on the energy mix for innovative power strategies. Energy efficiency is critical. AI-enabled power saving schemes are being continuously developed, and deep algorithms are working on it. Smart energy conversions, reduce energy and power losses. Water management, thermal and humidity control, lighting, record keeping, and research and innovation. These are the standard protocols which are specific to energy production. And in terms of 3D printing, we also work on various aspects of 3D printing which are very specific to the power station. And the material selection are very specific to the power station requirements in terms of certain dielectric materials, which are isolators. And we also work on certain conductive polymers which specifically are being used for the power station. Let's look into the calibration testing, and these are the various aspects we cover in terms of the printing process, quality control, and also in terms of the waste management. And these are some of the components which have been previously used in the International Space Station, and also in terms of some of the devices which are being produced for tools. These are the tools which we produce using 3D printing. And this is one of the material which is being 3D printed using the regolith, which is available in situ, helping us for further rigid structure construction, and which predominantly takes quite a lot of power. This is primarily based out of laser-based 3D printing. So we are fine-tuning the overall energy mix on various need-based situations. In terms of the technologies and outputs that could be applied to Earth, it could start from wide variety of aspects, right from space architecture, in terms of nuclear fission, nuclear fusion energy sources, kilopower, which is a decentralized power system, which is quite useful in rural areas, and battery technologies, which are extensively being used in mobility areas, in terms of energy sources, even back in Earth as no grid stabilization using peak power balancing using flow batteries, and various electrical and electronic sensors across the energy sector and also in various industrial applications. Carbon capture, which is primarily also is very critical back in Earth. Whatever technology we are using in Mars, which are very harsh conditions, definitely translate and help Earth in terms of doing the carbon-based energy sources. We also do a lot of electrical and electronic 3D printing components, right from PCB level hardware components up to bigger solar panels. And we also work on hydrogen fuel cells, which are quite highly efficient and using various sources, not only just hydrogen, but also methane and methanol fuel cells. Wireless energy transfer, which is very critical considering the long distance between Earth and Mars. The wireless energy transfer using high laser powers are being effectively used for the communication. Pulsar propulsion is currently under the research and also in terms of the nuclear propulsion in general. And we could see the overall TRL level, talking about various energy specific and other sources which can be kind of developed across different periods of intervals. And considering the guidelines to be applied to daily life on Earth, health and safety measures, new approaches to education, healthcare innovation and improvisation, guidelines for handling catastrophes and accidents, energy infrastructures, which are both the current centralized ones and the decentralized one, sustainable energy mix, energy efficient power transmission, energy backup devices, and at last, the most important thing, clean and safe energy. Let's look into the impact to sustainable energy, sustainable development goals from energy perspective. The industrial innovation and infrastructure, as we discussed on various aspects of energy sources. Training astronauts, which talks about how to impart quality education. Energy efficiency with respect to affordable and clean energy. Cities and communities benefiting out of sustainable habitats, sustainable energy sources, and how various needs are being fulfilled in the habitat. Waste recycling, responsible consumption of resources, which is very crucial. Being limited resources, availability of limited resources enables us to understand the importance of how resources are being valued back in Earth, and it's how to handle them and conserve them. Climate, which is very important in terms of taking action against climate changes. Partnership for the goal, which is what is our motto in terms of our habitat in Marte, and responsible consumption of all the resources which are available to us, which covers the major sustainable development goals which are known to us. These are the various references which are being taken from today's discussion. So OpenAI, which produces through the artificial intelligence in terms of large language models, supporting us in terms of coming up with innovative habitat designs, hybrid power systems as a permanent colony on Mars. We also have Mars Societies, MDRS, and also in terms of various instruments which are part of Jet Propulsion Lab. We have space.com in terms of nuclear reactor kilopower. Also from Mark Gibson, NASA Glenn Research Center. Energy storage technologies for future planetary science missions, TPL Labs. And we also have from Habitat Marte Greenhouse from Chief Marty and astronaut Vinay Pragati's references. With this, Chief of Power Station, Habitat Marte, analog mission 166. Thank you. This is my contact and social media details. Good, Sal. Once again, a very special day, International Astronomy Day. And with this, I would like to thank the team of and I'm concluding my presentation.